In today's video, I'm going to show you how this limit right here yields an unbelievably beautiful result. So let's get started. Now, some people, when they see this, might just think, oh, let me just plug in 0, right? Now, if we plug in 0, nothing is going to work, right? So let's just think about this for a second. 1 plus 0 to the power 1 over 0. Let's just treat 1 over 0 as its own thing. 1 over 0 is just infinity, right? So really, you're just going to be left with 1 to the power infinity. Now, I think the mistake that people make here is they think that 1 to the power infinity just equals 1. This is false. No, right? And the reason it is false is because of the fact that 1 to the power infinity is indeterminate, right? So you might think that just because 1 squared equals 1, 1 to the power 10 equals 1, 1 to the power 100 equals 1, 1 to the power infinity equals 1. But that's not true. It's indeterminate. Can't do it, right? So how do we do it? Well, it takes some algebraic manipulation, and here's how we're going to do that algebraic manipulation. So I think first and foremost, the best thing we can do here is kind of give this limit a name, so we can do things on both sides. Let's just call this limit L. L equals the limit as x approaches 0 of 1 plus x to the power 1 over x. So the first step here is to take the natural log of both sides, because that's going to allow us to bring the power down, which you'll see very, very soon. So this looks a little bit odd, right? ln of the limit as x goes to 0 of 1 plus x to the power 1 over x. There definitely is a way we can rewrite that, right? There is. So since the function ln is continuous, CTS just means continuous, on the interval 0 to infinity, right? Because we're not including 0. At 0, it is actually undefined. Since it is continuous on this interval, we can rewrite this. So our first part is going to be ln of, because this is the original part, limit as x goes to 0 of 1 plus x to the power 1 over x. And then we can kind of just flip these little two parts out right here, right? Bring one out of the parentheses, put the other in the parentheses. So it actually comes out to be the limit as x goes to 0 of ln 1 plus x power 1 over x. Cool, right? Now, this part right here, we're still rewriting things, kind of messing with things, right? This part right here is important. Knowing your logarithm rules are super, super helpful. If you have the ln of a to the power x, right, or x to the power a and vice versa, you can actually write it as x ln of a. So how can we rewrite this right here? We can write it as the limit as x approaches 0, 1 over x times ln 1 plus x. Cool. Let's bring it down here, right? And now let's kind of just further rewrite this real quick. Cool, right? Now, what if we were to plug in x equals 0 here? We're going to get ln of 1 over x, right? Now, ln of 1 is just equal to 0. And then if you plug in x equals 0, it equals 0, right? Since we obtain a 0 over 0, this is an indeterminate form. This means that we can use our good friend L'Hopital's rule on this side of the function, right? So let's kind of keep our ln of L on this side. But we can use L'Hopital's rule on this one, right? So now we can use L'Hopital's rule here, right? Keeping our limit sign, limit as x goes to 0, but taking the derivative of our numerator and our denominator gets us 1 over 1 plus x over 1, right? Now let's try plugging in for x equal to 0. Equal to 1 over 1 plus 0 over 1. Let's kind of do our work over here. 1 over 1 plus 0 over 1 is equal to 1 over 1 over 1. This just equals 1, right? Now look at this. We have ln of L equals 1, right? How do we get rid of the ln? We just raise it to the power of e. So e to the power ln of L is equal to e to the power 1. These are going to cancel out. We're going to get L equals e, right? Now we initially define this big limit up here as equal to L, right? So since L equals E, we can actually say that this whole limit right here evaluates perfectly to E. So this entire thing right here perfectly equals E. It's a beautiful, beautiful limit. And this whole work right here, this kind of algebraic manipulation a little bit, or just really algebraic work, gets us to the point where we can say that this limit equals e. And it's a beautiful, beautiful answer. That is how you solve this problem.